Okay, hello. Welcome everyone to Hack Fukuoka. This is the February version. We've got some interesting talks and discussion to deal with. So let me do a quick introduction and then introduce some of the speakers for today. So first up in Hack Fukuoka's Tech Talks is going to be Nakaly
Okay.
from Line Fukuoka.
Yes.
Yeah. Just tell us quickly a little bit about yourself.
Okay. So this is Nakaly. So I'm an agile coach at Line Fukuoka, and I also a server-side engineer. So actually, I've been working as an agile coach for 2 years, and I decided to kind of move my career again, server-side engineer. So yeah, then kind of I just resume my hackathon project right now to practice my engineering skill. Yeah.
So this the project we're going to have a little show and tell of today is a hackathon project.
Yes.
Great. When did you make it?
So last year we had a hackathon in summer.
Mm-hmm.
So yeah, because of the COVID-19, we couldn't gather,
Yes.
but we just have a hackathon online.
Right.
So,
Okay. So we're going to hear all about your Slack ChatMap and visualizing these social connections. So yeah, please show it, and I'll switch the stream onto the screen.
okay.
Go ahead.
So yeah, let me introduce my hackathon project. So actually, the original idea came from him, Hirai-san, but he's busy today, so I will introduce on behalf of him. And this is agenda, but just explain what it is and show the demo. Okay. So what Slack ChatMap is visualize the people collaboration or communication from Slack chat. So you can, I think, you see the social graph of the Twitter or Facebook, so the follow or friend relationship, and you may want to see similar things at work. So I just explained the first motivation that why we made it is for peer review. So C review is our company's peer review. So it's kind of not quarterly, twice a year. So we sometimes remember whom we talked at for example, at the beginning of this year. But if we kind of visualize the relationship from Slack, then we just know that whom we talked to. So, and because of the work from home situation, we use chat more. So that's why we made this project as a hackathon project. Basically, we collect the Slack posts and reactions and save it in the database. So message, like if you mention someone in the post, then it means that one relationship from you to the person. And reply means thread. So if someone posts and the other person writes the other post in the thread, then there is a relationship between them. And reaction is also kind of relationship. So the application just use this data to make the graph. And the front end, we use a library called this.js. So then, we just visualize the relationship. So then, actually that's everything. So I just want you to see the demo. So since I deploy it in kind of unstable environment, so demo might not work. But this is kind of the whole picture. That's what I made. So basically, if you want to visualize the relationship, you invite the chatbot into the channel. Then the bot collects all posts and reactions. Then based on that, we can make this graph. So and if you want to kind of dig into the details, then we can kind of specify the chat channels, like then yeah, we can see the communication only the checked channels. And if we include the reactions, then of course we can have more relationships. And yeah, these, and let's look at more big channels. Like this. So actually, it's just a hackathon project, so the performance isn't so good. It takes time to render the graph or retrieve information from the data. Okay. So yes, you can see, so in this graph, there's a people kind of work as a hub. So maybe he's a leader or something. And yeah, interesting thing is our work environment is kind of bilingual environment. So the translation bot have a lot of relationships. And basically, the kind of the edge node, graph edge node is, they are kind of guest of the channels, and the kind of main person should be have lots of relationship in the channels. So maybe we can do graph mining things using this data, but yeah, what I'm doing now is just visualize it. So one more feature is we can, for example, I mean, the first motivation is want to see the people who I talked to. So I can specify the relationship of one person, like me. So get ID. Yeah, then I can just see the relationships around me. Yeah. Yeah, basically that's everything.
Okay, great stuff. Thank you so much for showing us your hackathon project. If anyone has any quick questions, please feel free to just post a question on the YouTube live chat and we'll read it out and ask it. I'm curious, were there any interesting patterns you noticed, or maybe things you didn't notice before that you noticed with this tool?
Okay. Basically, we just, the things that I see in the graph is as almost same as I expected, but yeah, I mean, different teams have different communication paths. Like, yeah, my team, no, I shouldn't specify. Because of the number of people are not so many, but, oh, it takes time. But
what's happening there?
I don't know. It's caused by the front-end framework. So,
Right.
But if there is a kind of relationship, I mean, all nodes connect to the all nodes, then it happens. But if there is a person who kind of work as a hub, then yeah, we can see the
Right. Yeah.
different shape of the.
I mean, Slack is a tool that so many people use now. Is there any chance we can use this tool to check out our relationships on Slack?
I think everyone can use it. I mean, there's no confidential things in that code, so yeah.
Oh, that sounds fun. Hopefully, if we get a link to it later, I'll put it up on the event page or on the YouTube so people can find it. Wow,
Okay.
really cool little project. I liked it a lot. Thank you very much.
Yep.
Okay. Sorry, at the beginning, for everyone watching on the stream, at the beginning, I didn't introduce myself very well. So let me do that now, very quickly, while we change speakers too. Whoops. So thank you very much, Nakaly. I'm Laurie Griffiths. I'm a community manager here at the Engineer Cafe. And the Engineer Cafe is a free co-working and maker space provided by Fukuoka City for everyone in Fukuoka City to use. So, for example, you can come here and do making things down in the makerspace downstairs, or you can come do some co-working and coding upstairs. We also have lots of people, community managers, ready to answer any kind of coding questions and ask them things about programming and learning how to do this stuff. So, as if by magic, I've switched speakers to a new speaker, Pierre.
Hello.
Oh, we just having some trouble seeing you on the screen there. I wonder what happened. Let's see. Just a bit of tech support here. I think we just got to get the TV on the correct channel. Let me see if I can see it. We can see it on the stream, so we just can't see it on the TV. Yeah, so while we're fixing this tech trouble, I'll just introduce Pierre. Pierre, tell us about yourself. Are you you're an AI, working with some AI stuff in our presentation today, right?
Today I'm gonna make a presentation about reinforcement learning. So I don't know. Okay. Can we exchange with the people attending, or
so
how does it work?
People, we've got a live question, so people are asking questions on the YouTube, and I will try and look. I do realize someone has asked a question for Nakaly, the previous speaker, about how long the project took, so maybe we'll come back to that at the end when we all come together for a bit of discussion. So don't worry, I have seen your question. It's a loose connection at the back. We can see you on the stream, so, there it is.
Okay. I think that's
it's gone.
Maybe the connection.
I think the cable's just a bit loose, but we can see you fine on the stream, so if you want to start your presentation, please feel free to do so.
Okay, sure. So
we need to get your slides on here, though.
Oh, where is it?
It's looking good. It's looking good.
Because it's like
whatever you see on here will be what's on the stream. So we need the slides on this screen. Yeah, if you have any general questions about Engineer Cafe and the things we do here, you can put those on the stream as well. So,
like
presenter mode, maybe?
I already.
Maybe just drag the window onto this one. Or.
Okay, maybe.
Yes, unfortunately today we've been very busy. We had lots of TV crews in and out.
Cool.
We didn't quite have enough time to do a full tech run through, so we're doing it live. Okay.
Cool.
That's great. Looks good. I think you said, we're going to have some slides and some demos. Please, Pierre, take it away.
I guess later. Okay. Cool. So to introduce myself, so I'm Pierre Guinaudon. In my last project, I co-founded and was CTO for 5 years in a tech startup, which did AI for anti-counterfeiting. So I was working computer vision and using pictures taken by users that they were taking of a product to see if the product was real or faked based on this picture.
Cool.
Recently, so I'm learning about reinforcement learning, which is another area of artificial intelligence, and as I'm learning about it, I'm really interested about this subject. Maybe I can share a little bit with it, and give a small introduction to people who maybe don't know what it is.
Brilliant.
Okay, so all right. So during the talk, I'm just gonna do a quick introduction about what is reinforcement learning. Give a quick presentation of how it works. So without getting too deep, but talking a little bit about the algorithm, and then making quick demos to show what we can do very quickly with this kind of technology. So first, I guess maybe many of you have heard about supervised learning. Well, I don't know what's the experience in AF?
I think many people watching are maybe engineers, but not necessarily AI engineers. So if you could explain some of the basics for us.
So first, reinforcement learning is another area of intelligence, artificial intelligence, that kind of opposed to supervised learning. So in supervised learning, we had algorithm to detect, for example, like if you have a problem, you want to classify pictures, like say if a picture is a cat picture or a dog picture, then we already have like algorithm that do that very easily. And the way you do that is you'd have a bunch of example pictures that I already tagged. So you have a list of pictures which are, or you know, are cat pictures, and a list of pictures which you know are dog pictures. Then you'll train a model based on what you know, and then you can use it on new pictures which were not part of the training base. So this works for a lot of problems where you have actual already like training data. So you need to already have pictures that you know are dog picture and cat picture. But in the real world, if you want to solve like a real world issue, in a lot of cases, you're going to have to take a sequence of actions, like not just one action or one classification. You're going to have to take a sequence of action to try to achieve a goal. Mm-hmm. And you don't necessarily know when you take the action, like whether is it like a good action to go towards your goal or a bad idea. Like, and you can take like life as a real example. Like, for example, if you're gonna start a business, you know, you're trying to sell a new product. Is it going to work? Is it not going to work? But maybe you only know 10 years later whether like the action you took before actually gave a good result and positive result, and it can take some time. So supervised learning basically is a range of algorithms that try to solve this kind of more complex problem where you're going to take a succession of action in the environment without necessarily knowing in advance like what's the reward is going to be. So there's a notion of cumulative reward, meaning that the reward can be delayed, and it's sometimes only after you take a series of action that you're going to know if this series of action was successful or not. Right? So possible applications, like for example, self-driving cars, robotics, or if you want a robot to act in a certain way and take complex action in the environment, and of course, like the most well-known example is games, because in games you're gonna have to take a series of steps, and you only know at the end of the game is if you win the game or not. So for example, in this area, I think people have probably heard of project by Google DeepMind with AlphaGo or AlphaStar, like if there are some StarCraft players, or maybe also OpenAI. They have the gym environment where they offer like lots of environment, including like video games or old Atari games where you can try some reinforcement learning to play these games. So how does it work? The basic model of like a reinforcement learning agent is like, so you have an agent and the environment. So the agent is going to take a succession of steps, so action towards the environment. So for example, if you're playing a game, the action will be like which move you decide to do. So let's say you're playing Go, like where you're going to play the stone, or if you play chess, like which piece you're going to move, and so on. And then the environment is going to change based on the action. So if you played here, like maybe the board state is going to change, of course. And the agent is going to observe like the new state of the environment and receive a reward for the action they took. So this is like the immediate reward. So if you take, for example, if you're playing a video game, maybe the reward is like a score, like the score. Like let's say you're playing Mario and you get a coin, then your reward is going to increase. And it's also possible that the reward is going to be 0 for the whole game, and only one, like you're only going to get a reward at the end of the game once you win the game. So that's the whole point, is that you want to take into account not only the reward that you are getting now, but also like the cumulative reward that you're gonna get through the whole game or episode. All right? I hope it makes sense. Are there any questions so far, or?
No, everyone's listening
I don't know
quietly
if
at the moment.
I hope I'm clear enough. So in order to like try to evaluate the cumulative reward, we introduce a notion of Q function. So that's why you also hear about like deep Q learning or Q learning. So it's a class of reinforcement learning, where you use like this Q function, which is basically the Q functions is like is the expected reward for an action in any given state. So it takes into account the state of the environment, of course. So you have to look at like what the environment is like what the game position is it, like, and you have a list of action you can take, and you have to choose like you want to choose like the better action. So the Q function basically it gives you like what's the value of taking this action at this specific time when the state of the environment is like S. And obviously you want to maximize the Q function, so you're going to select the action which is which give you the highest expected reward, if it makes sense. And one interesting property of this Q value is that you're gonna want to take into account like both the current reward and the future reward, and so that's why it has to respect this equation. So this is like R is like the current reward you're gonna get from taking the action in the state S, and then it's gonna also have to take into account like all the rest of the reward like for all the next moves, and this is the Q function of so S prime here is like the next state of the environment after you take the action, and all the new action you can take after this state. Does it make sense, or?
Yeah.
So the Q function, you want the Q function to be equal to like the immediate reward and the future reward. And the discount factor here is a discount factor you use like to avoid having like infinite reward in the future. And basically what it means is like whether or not you want to prioritize like a current reward, so you want like more stuff now, or like you want to be more long-term, like the higher it is, the more kind of long-term vision you're going to have, and like the lower it is, the more you're gonna prioritize like the current reward, like immediate reward.
Can I ask one quick question?
Yeah,
when
of
you
course,
say infinite reward in the future, can you explain that?
Yes. So if you didn't have like this this parameter, like potentially, well, it depends on the type of game, but if it's a game that potentially can last indefinitely, then you could get like infinite, like for every move. Let's say like every move you can get 1 point of reward. You could potentially like infinite reward if it lasts like forever. So this is a way to kind of exponentially decrease the reward as time goes by. So it's also kind of a way to show like uncertainty, because the reward you're going to get later is like more uncertain than the reward you are getting now. So you always prefer like having getting one now than one later.
I see.
But of course you'd prefer having maybe 100 later than one now. And this is kind of the parameter that decides like whether or not you prefer, like how much you're ready to sacrifice immediate reward, like to get a better reward later.
Right, got it.
Yeah, so hope it makes sense. So then the problem, like the main problem in reinforcement learning is like, okay, it's good if you had this Q function that tells you, okay, if you know, I have this this board, like if, for example, for a game, I have this state of the board, and for each action, I know what's the expected value. So if I know the Q function, basically I've solved the game, right? Because I know what's the best move in every situation. The problem is obviously we don't know the Q function at first, and the whole point of reinforcement learning is going to be to train a model to like approximate the Q function as best as we can. So for that we are going to select a model for the Q function. So in a lot of cases can be a neural network. So that's why reinforcement learning uses also like older models from other problems, like convolutional networks or deep neural nets. This model is going to be used to approximate as best as you can the Q function, and then the agent is going to interact with the environment, so play a bunch of games or simulate a bunch of games with the environment, and like record like the reward they get, and update the parameters like slowly at each iteration, slowly update parameters of the Q function in order to better approximate the model. Just a quick note on two points that are important for when doing reinforcement learning. There is a notion of exploitation versus exploration. This means like when the agent is interacting with the environment, you want to sometimes take random actions, like try new action which you haven't tried before. So usually that means like taking random actions, and sometimes you want to take actions which you already know are good. So at the beginning of the game, at the beginning of the training, I mean, the Q function is like random, so you're very bad at the game. So you want to take like just a bunch, as many new actions as possible, because you know you're not very good at the game for the moment. But as the game progresses, if you keep making just random move, you're not gonna learn like more complex strategy or complex possibilities. So you have to find a balance between making good moves, which you already know are good because you already learned, and a random move. And the way we do that is like using epsilon greedy policy. So it means basically at the beginning of the training, you always take like new actions or random actions, and as you go and as you get better, you want to decrease the rate, like the percentage of random action you take, and make more like good moves. So moves you already know are good. A second important point is experience sampling. Is that when you're training the Q function, you don't want to only update it based on the result of only one game. You want to take random experiences from a bunch of different games, so you don't get biased towards one game, and you have like more, I say like a more representative set of sample. So yeah, this is like a quick, it's like very summarized, but like an idea of the learning process. So the agent is going to interact with the environment during what we call an episode. So episode is basically a game. So you, from start to finish, so to the end of a game. So it doesn't have to be a game, but it's like basically from starting state to end state. You'll record all the reward, like after you take the actions, you'll record the reward you got and the new state of the environment. You record that you record all these transition, and then make the random sample of this transition, as we said. Use them to compare, like to calculate the loss. So basically, loss is you compare what's your expected reward using your Q function, and what's the reward you observe based on so immediate reward and the Q function, so the value of the next state. And you want to minimize to make sure that the expected reward and the actual reward get as close as possible. And so you'll slowly change the parameters of the Q function model to get them as close as possible. So this is the way you update the parameters is basically the same. You can do a gradient descent, for example. It's like the same as any algorithm that uses neural networks. Any questions? I don't know if it's. I hope I'm making sense
so far. Yeah.
Okay, and then you repeat the process until the Q function, like the Q function model, gets better and better at approximating the real model of the environment. Yeah, so let's do a quick demo.
Great.
Wait, I'm not used to the. Where is my? I'm not used to the two-screen system. How can I get my mouse back?
Maybe left or right.
Yeah, I tried both, but oh, okay. This way works.
More tech trouble. It's my fault.
No, it's my fault.
Okay, so we got two demos here. I guess these are simple games, right?
Yeah. So the first is the pole cloud problem. It's like the very basic environment if you want to like try a reinforcement learning model. It's like well, I'm gonna show it. It's like better. Can I? Not sure. I should move to the right, I guess.
Yeah,
Sorry about all this.
That's okay.
Okay, I'll just shut down the. Okay. I guess
Yeah,
shut this down for a moment.
Any other questions from the chat?
Yeah, please, if you have any question,
jump in.
because I don't know like, if I'm clear, if I...
Okay, here we go. Nice. Let's put the demo up.
Okay. So...
Can you make it slightly bigger, maybe?
Yeah,
For
sure.
font size? I don't know.
All right. Just to show you like what the poll card, I'm just going to run it quickly so you see what it is. Oh, it's on my... Okay, wait.
Is there any way to make the,
No,
the font size bigger for the demo? Just a little bit?
Let me try to put the... Okay, because I have another window here. Okay, this is the cartpole problem. So the cartpole issue is basically you are trying to balance a pole by pushing the cart under it either left or right. So the agent has to decide like whether to push right or left to try to balance the pole as long as possible.
Right, so it's a little bit like getting a broom handle on your hand and
exactly
just going
like this.
backwards and forwards.
So basically the like physics system is simulating the environment, and at the beginning, so the agent will just randomly push left or right, and you want to train it so that so it manages to keep it balanced as long as possible. So you see, like,
so you start with no physical rules, no kind of physics.
Absolutely. It's like totally from zero. That's why that's why interesting with like the reinforcement learning. It's like it starts like completely randomly. So we initialize the parameters of the model completely randomly. So just to show here, the model, like, so this is using Keras. So Keras is like a very famous artificial intelligence library for Python. So here, this is like the model we'll define for the Q function. So in this case, it's just two layers of neural networks. So so one layer with 16 neurons, like the entry number of entry parameter is the like observation space, and so the observation space is like like what we read from the environment. Sorry, so it's like the state of the environment basically. So we observe the state of the environment, put it as an input, and then as an output we give like the value of the expected reward for each of the possible action. In that case, there are only two actions, like push right or push left. Up. Oops, where is my window? I'm not used to. Oh, here. No, that was. Put it in the background, but. I don't know. I don't know what
Joy of live demos.
So
can you get it back?
Yeah, I'm just gonna run it again. So I mean, I've sent in the presentation. I've sent a link to a blog which has a tutorial that I use to do the demo. So if you want to do it yourself,
great. And I'll put the links up in the YouTube description and in the event pages.
So please, it's like this is like a very simple. A way to give it a try if you want to have a try at reinforcement learning. So basically what we do is just if you want to know the code, we get the environment from Jim. So Jim is the OpenAI it's the OpenAI environment where they already developed a bunch of environments. You can go and check it out like to solve like a certain problem. So this is one of the problems they provide. So we define the model and we train the agent and then test it on a series of episodes.
Yeah, just a few questions from the stream.
Yeah.
One person's asking, well, Python. Is it Python? Can you talk a bit more about the versions of things you're using? So is it Python?
This is Python 3.7, I think.
Yeah. And
3.7, Keras 2 point something.
Great.
I'm using library I'm using here is a Keras RL. So here.
Okay, so that's a reinforcement learning.
Yeah, it's a reinforcement learning library like for Keras, which I'm using here.
Okay. Yeah, there's another question. Would you suggest creating a custom network from scratch or using a pre-trained model for reinforcement learning?
Say again?
So do you suggest using a pre-trained model for reinforcement learning?
So you mean like, okay, I understand what the question is. So you mean either like training really from zero, like we're doing now, or having something that can already kind of know, okay, that knows something. Well, I guess you can do both. It depends on the application. Like, for example, like DeepMind when they developed like AlphaGo, so the software to play Go, like at the beginning, what they did is like they did exactly what that like the person said. So they first trained it on games from like well-rated players. So they start like having a kind of a base level artificial intelligence that was trained on good players. Of course, if you only train on good players, you can only get as good as human player. You can never beat a human player. But then they use this as a starting point to continue training and then make it like play against itself to become like to beat like the human player. But then they made a new version of it, which started like completely from zero.
Oh, so the new version,
which was
no training on games.
Which was absolutely with absolutely no training, and so I guess it was like in that case the idea was more like is it possible to, it was like a challenge, is it possible to have an algorithm that starts from zero?
Yeah.
So I guess the answer is like you can do both, and it depends on the application.
Answer, yeah.
But I mean, it definitely, yeah.
The pole cart example is just trained from zero, nothing.
Yeah, this is like this is a very basic example. So
yeah, one more.
You can see like you can just take a look. For example, like at the beginning of the training, like the number of steps is like pretty low, and then as it as it gets trained, like in the so this is like the last training steps, then this gets higher.
Okay, great. There's one extra question.
Yeah.
If you trained the model in an environment, can it change the strategy, change the model drastically based on another environment?
All right. So
I think that's from Nakaly over there. So if you want to ask your question again.
It's kind of based about overfitting or overlearning.
Oh, so if we overfit the training on one environment and then we try it on a new problem, does that cause other problems? I'm not sure.
I'm not sure I understand the question. Sorry, can you? Yeah.
So if the opponent has maybe just one strategy,
Yeah.
then the model learns how to win But
Yeah.
if the opponent changes their strategy, then maybe the model also changes their strategy. So it's possible to change the strategy while the game is ongoing.
Let me repeat that question just for people listening at home. So,
okay.
The question was if you're playing a strategy game like Go, and you have a sort of strategy to win the game, and the player you're playing changes the strategy, can your model change the strategy halfway through? I think that's basically what the question was.
Yeah. Okay, I understand. So I mean, typically it's not what you would do. I mean, in the sense that the model you train is already takes into account the state of the board. So I guess the strategy of the opponent is going to already be visible or be indirectly taken into account, because the state of the board will be different based on what your opponent is doing. So in a sense, yes, it's taking it into account, but it's like the same model which is used anyway.
I see.
But yeah, it's a very good question in the sense that you have. I mean, it comes back to like the exploration versus exploitation, in the sense that you have to you have to try, like you have to test like a whole bunch of the, like you have to make sure you continue testing like a whole bunch of new strategy, because else you could be stuck in a kind of a local optimum, which like your AI found like a good strategy at their level, but if they don't continue exploring like a new strategy and trying like new moves which they didn't think of before, then maybe they get stuck into this and they don't explore like maybe more optimal strategy.
Right.
So
Great.
yeah, that's a good question.
Thank you. Okay. Did you have another demo?
Yeah, just for fun, actually, to show you can. So this is using like the gym model, and I just quickly like make tic-tac-toe an AI for tic-tac-toe, just to show you how you can make like something simple. So I'm just gonna play. Wait. Or maybe do we have time, or maybe
yeah, we got time. We got time.
Okay.
Do it. Hopefully it works.
No. It's like it works. That's not a problem.
Sorry,
just like maybe I don't need to get into like a lot of details. But
well,
I just thought it was interesting maybe to see how you can like use the gym framework. So gym has a kind of a model class for environment. So an environment is basically like the rules of the game, or the rules of like the problem you are trying to solve. So with like a bunch like the API contains like the step function is like where like how you change the state of the environment when you take a step, and what reward you're gonna get. So it reiteration of the new observation of the environment after you take the action, like the reward you get, whether it's finished and whether the game is finished or not. So this is an implementation of the environment class if you want to create your own like games and rules and things. And I just for a test I did like a tic-tac-toe game. Play. Okay. Let me just. So I wanted to see. Like how it would work if we first have an opponent which plays randomly. Okay, let me just run it, I guess. So while it's training, yeah, this is maybe the part which is interesting. So I'm defining kind of the environment. So two things you have to define is like the action space and observation space. These are like two interesting concepts. So action space is basically how many actions and what actions you can take. So in that case, like we have a discrete. This is like just a function from G. It tells like it's a discrete number of actions. So like a limited number of actions, limited to the grid size. So grid size is like the 3x3, so 9. Grid size here is equal to 9, because basically the action you can take in tic-tac-toe is just select the square and like play there. And the observation space is like basically the grid, so the nine squares of the grid with like a value. So I've selected 3 different values depending on if it's empty, it has like a X or a O inside. So this is what you have to define when you fill up the game. Oh, it didn't run? Wait. Oh, no, sorry, wait, I took the wrong one. Yeah.
Okay.
I ran the wrong one, yeah, okay, sorry. So first I like,
We've lost the screen, hang on, sorry about this. I have no idea. Is your computer okay?
I think so. Oh, unless I don't have battery. Oh, wait.
Hang on.
Maybe it's like, I think, okay, thanks.
I think the battery might have run out.
Yeah.
We've got a solution. Bear with us.
Sorry about this.
That's okay. Mind the microphone.
Yeah.
Brilliant, thanks. Okay, we'll try and get this demo on as soon as possible.
Do you have any other question in the meantime?
Yeah, are there any more questions about the demos or about the coding, Python and Keras? If anyone wants to ask anything. Oh, here's a question. Do you need an expensive GPU or CPU for learning? it seems everything runs on your machine.
Yeah, I mean, this for basic stuff like this, you can totally run it on your machine. After, there are lots of like cloud service you can use that will do the training in the cloud. If you want to do like, of course, if you want to do like more resource-intensive training, there are lots of services in the cloud which you can use. But like for learning and just doing a quick demo like this, you can run it on your computer. Like this is like running my computer.
Okay, great. So we're back on the stream. So please explain your demo. What can we see?
Oh yeah. So right now it's like it's in the process of training.
Okay.
So you can see each episode. Like okay, let me stop it for a moment. Like each episode, you'll see the number of steps before it ends and the reward. So in that case, 1 is for a win, 0 is a loss, and 0.5 is like for a draw. So this is like a reward I set to train it. I guess if we go back at the beginning, we'll have lots of 0. Because also, like if the AI tries to play in a square which already contains something and they cannot play in, it's going to be a loss, automatic loss. So the beginning, we're going to have lots of zeros. I guess I can't go all the way back up. But
so it starts off making a lot of mistakes.
Yeah, making lots of mistakes. Yeah, exactly.
0.
And I don't know. I guess it's just some. Oh yeah, here is like some test game, a bunch of test game they play at the end, like to see if like they've learned something. So, and for all the test game you see is like 1, so it means they won the game. So they managed to find a basic strategy, which is like first don't play where you were in an empty square where you can play, and then they managed to make like a line even when the opponent like starts blocking the line where they started. They managed to get around, and you can see like find a way to find a straight line. Like even here. Their first line was blocked, but they managed to do one.
So playing tic-tac-toe very well now.
Yeah, I mean, this is against a random opponent, so it's kind of easy. But then I just tried to make a different kind of opponent, which instead of just playing randomly, which is kind of easy, like at least try to counter. Like if they see that you're about to win in some way, like have 3 in a row, they are gonna do their best to block you.
Right.
So it's like. We can see if the AI evolves to take it to like develops new strategy like facing this new kind of opponent. Yeah, it's gonna take a little bit again.
One more quick question: what IDE do you use?
This is like PyCharm.
PyCharm.
Okay.
Awesome. Yeah. There you go. PyCharm. Nice, easy question. So training, how many rounds of training?
This is like 20,000.
20,000, wow. And hopefully...
Well, it's not, it's 20,000 like round of training, but it's less episodes. Because after, like an episode is like basically a series of action until the end of the game.
So one game.
And then it's gonna add it to like the sample, sample database. And then whenever it updates like the queue function, it's gonna sample randomly from the database, so from all the previous games, not only the last one, but all the previous games.
So we're running up against the clock now, so hopefully...
Okay, sorry.
Here we are.
Up. So yeah, in that case, so you can see in that case, like adapt its strategy to like, it's gonna have to trick the opponent. Up.
So what's it doing here?
Up. Let me find a good example. Like for example, in that case, it not only has to just find a 3 row in a like to do like 3 cross in a row. It also has to find a way to have a kind of a double to threaten it twice at the same time, because else the opponent is just going to block. So for example, here. You see like the opponent, so I started here, the opponent played here, and the AI like kind of developed a strategy to force the opponent into like a double threat, which they couldn't get out of. So first by playing here, forcing the opponent to play here, and then when they played here, you see like they had both like this line and this line threatening both this line and this line at the same time. So if you see like the AI like kind of evolved this strategy to find this like double thread to.
So it's playing
thread on
now
AI.
much like a stronger
Yeah,
game
it's
because
like
it was
stronger because you gave it a stronger opponent. I guess, so.
right.
I think so.
Excellent. That's a wonderful little demo. I like
Okay.
it. So we're kind of running out of time here. If anyone
Yeah.
has any quick questions, put them on the stream. But I have to say thank you again to all our speakers today, Pierre and Nakaly, who did a great job showing us some really cool little things. Yeah, and if you're interested in the Engineer Cafe, please come along. We're open every day until 8. And we're here to support all the engineers in Fukuoka. But yeah, that's everything, I think. So thank you for watching at home, and thank you for everyone here. And goodbye. Yeah.
Thanks. Thanks, everyone.